Okay, in this video we're going to put together everything we've learned so far in order to make a shear moment diagram for this beam. Obviously the loading situation here is significantly more complicated than in the previous two examples, but the process is the same. So as long as we follow the same process, we'll still arrive at a proper shear moment diagram. So again, the shear diagram goes down directly below the load diagram. And we're going to start off with a horizontal line that represents 0 kips of shear. So this is our shear diagram. We're starting off 0 kips. And the first load we encounter is the reaction supported A. So we go from a value of 0 up, up, up to a value of 36.8. Okay, then as we begin to travel across the beam, we encounter this distributed load right here, which is going to push our shear diagram down at a rate of 4 kips per foot. Well, 4 kips per foot spread out over 10 feet would be 40. So that means that if I draw a line straight down from here, I'm going from a value here of 36.8 down, down, down to below the horizontal axis, because I started off with 36.8. I subtract 40 from that, and that leaves me with a negative value. It leaves me with negative 3.2. So that is the shear value at this point, negative 3.2. Now I'm going to want to know how far over was I when I crossed that 0 axis. What is this distance? That's going to be important to know when making the moment diagram. So if I start off with a value of 36.8 kips, and I divide that by 4 kips per foot, I end up with, that's going to be 9.2 feet. So 9.2 feet over from the left support, I'm going to hit a shear value of 0 and then continue down until I hit a value of negative 3.2. Then for the next 5 feet, I come right down here. There's nothing going on. There's no load in this area. So the shear diagram is going to remain at a constant value of negative 3.2 until I reach this point where we apply a downward force of 8 kips. So I'm going to go from a value of negative 3.2, 8 more kips in the negative direction, and that's going to leave me with negative 11.2 kips of shear. So negative 11.2. And then I'm going to travel horizontally. Nothing's going on in the diagram until I reach this point, at which I encounter another negative 8 kip load. So that will take me down even farther. I was at negative 11.2. I go 8 kips further down, and now I'm at negative 19.2 kips. Negative 19.2. And don't encounter any more loads until you get to the end, support B, where we have a reaction force of positive 19.2. So that's a good sign. That means that I was at negative 19.2. The reaction force is 19.2, so that brings us back up to a value of 0. When we start and end at 0, that means we did it right. If we get to the end and our shear diagram isn't closing, then we need to go back and look for potential mistakes. So I can shade in the diagram here. This is where I'm experiencing positive shear up until the 9.2 foot mark, and then from here on I'm experiencing negative shear. create the moment diagram, we're going to have to come down and draw the moment diagram below, directly below the shear diagram. Okay, so I start again with a horizontal axis representing 0 moment. And if I look at this first portion of the graph, I start off with a pretty high slope. Remember that the value of the shear diagram equals the slope of the moment diagram. So I'm starting off with a high moment. It's going to take off like a rocket, and it's going to slowly decrease until at this point that's 9 feet 2 over, the shear diagram hits 0, which means the slope of the moment diagram is 0, which means it's horizontal. It's tangent to a horizontal line. So in other words, it's peaked at this point. Then the slope is going to continue to or start to decrease. We're going to have a little bit of a negative slope, and then it's going to get a little bit more and a little bit more and a little bit more negative. So there's a slight little curve in this part of the diagram until it comes back down to some value. So let's back up here for a second and look at this maximum moment value. The value of the moment diagram is equal to the area of the shear diagram. So the area of this triangle, that first triangle in the shear diagram, is 1/2 base times height. 1/2 the base is 9.2 feet, and the height is 36.8 kips. And so that equals 169.3 kip feet of moment. So this maximum value, I want to label that on the diagram, 169.3, right there at that point. And then it begins to slope downward. It curves down a little bit to this point. What is the value on the moment diagram right here? Well, I have to subtract from that value, that maximum moment value, the area of this triangle. If that was 9.2 feet over there, this is going to be 0.8 feet over here, because the total span to this point, to the end of the applied load, was 10 feet. Okay, so the area of that triangle is going to be 1/2 times the base is 0.8 times the height is 3.2. And that equals approximately 1.3 kip feet. So if I'm starting off at 169.3 and I'm losing or going down 1.3, that means the new value is 168. Now let's look at this next section of the beam over the next distance here. And this is a distance of 5 feet from here to here. The value of the shear diagram was negative 3.2. So if I find the area of this rectangle here, it's below the 0 axis, so it's a negative value. It's going to cause my moment diagram to go down. So it's going down, but it's going down at a constant rate. The value of the shear diagram here is a constant 3.2. So this is a constant slope. This is going to be a straight line from this point to this one. And if I want to find the value here, I need to find the area of this rectangle. The area of that rectangle is just the base times the height. So the base is 5 feet. The height is 3.2 kips. And so that is 16 kip feet. So the value here would be 168 minus 16, and that gives me 152. So I've come down in the moment diagram value from 168 to 152. Now let's look at the next section of the diagram. Again, we're sloping down in a straight line because the shear value is a constant value, which means I have a constant slope, which means it's a straight line. The value of the shear diagram here is 11.2 feet, and the width of this area is, again, 5 feet wide. So that's another 5-foot length of beam. And so the area of this rectangle is equal to its base times height. So that area is equal to, the base is again 5 feet. The height is 11.2 kips. And so that's equal to 56 kip feet. So if I look back at the diagram here, I had 152. I subtract from it 56. And that brings me all the way down now to 96. So the value here is 96. If we look at the very last rectangle, again, the width of it is 5 feet. So we're dealing with another 5-foot length of beam. This time, the height of the rectangle, this rectangle, is negative 19.2. And so the area of that rectangle is 5 feet times 19.2 kips. And 5 times 19.2 is equal to 96. That's a good sign. That means we did it right because we had a value of 92. That last little bit takes us down to 0, and our moment diagram should begin and end at 0. So I know that the picture here is not great. I'm not going to be grading you on your artistic ability, but what I am looking for are the basic shape. It curves up in this first section. So we've got a curve here, a little bit of a curve here as well, and then from then on, it's straight line segments. Straight line from there to there, straight line to there, and then it finishes off with another straight line. And the other thing that's important are these numerical values. Maximum moment is occurring at this distance of 9.2 feet from the left support, and that maximum moment value is 169.3 kip feet. And then it reduces to 168 kip feet, and 152 kip feet, and 96 kip feet, and then finally at the right support, 0 kip feet. Those are the important values I'll be looking for when grading these diagrams. The maximum shear, it doesn't matter if it's positive or negative, we're looking for the maximum magnitude. So on the negative side, the biggest it gets is 19.2. On the positive side, 36.8. Obviously 36.8 is bigger. So in conclusion, we would say that the shear max is equal to 36.8 kips. And that occurs at the left support. The maximum moment, the M max, is equal to 169.3 kip feet, and it occurs at a distance at 9.2 from the left support. Okay, so that's what these diagrams tell us. That's why they're important. So we know the maximum moment, the maximum shear and the maximum moment and where they occur. That will be necessary information to know when we design these beams.